This lecture, we're going to look at what happens to massive stars when they come to the end of their lives.
So what's going to happen to the final iron cores of massive stars? Well, just to remind you of the final stages of nuclear burning, we have oxygen burning to silicon, and then silicon burns to iron, cobalt, and nickel. The iron is the dead end. No more energy can be extracted from iron via fusion reactions. What happens is that silicon keeps burning to iron in a shell around the ashes of iron in the center of the core. This core is about 500 kilometers across. And so you have iron constantly being generated by silicon burning, and so this iron core starts growing and growing and growing. When it reaches a certain mass, known as the Chandrasekhar mass, which is about 1.4 times the mass of the Sun, the pressure of the degenerate electron gas inside the core cannot hold the core up against gravity, and the iron core starts to collapse. As the iron core collapses, electrons and iron nuclei get squashed together. Electrons combine with protons in the nuclei to form more neutrons. This decreases the pressure and speeds up the collapse, since it was the electrons that were providing most of the pressure in the first place. The collapse itself takes only a few thousandths of a second. When the core reaches a size of about 50 kilometers, the material is a degenerate gas of about 70% neutrons, 30% protons, and the temperature is about 100 billion degrees Kelvin. At this point, the pressure of the gas at the center halts the collapse. The core is now what is known as a proto-neutron star, about 50 kilometers across. It contains still about one solar mass's worth of material. The outer layers, however, are still falling in on top of this proto-neutron star. When the electrons get captured by protons, they turn into neutrons and neutrinos, and these neutrinos are streaming out from the core. A vast stream of neutrinos flows out from the proto-neutron star. So what happens next? Well, here's the outer envelope of the star, here's the iron core, and the inner part of the iron core collapses. The proto-neutron star is created in the very center. Material is falling down on top of it, and it hits the neutron star and bounces off of it. So the red material, it bounces off of it and starts rebounding outwards. This outward traveling material meets material that's still infalling from the outer part of the core and creates a shock wave. What usually happens is this infalling material from the outer part of the core stalls the shock and causes it to stop. But then so many neutrinos are being generated in the very core of this proto-neutron star that they actually heat the layer of material around the stalled shock. And that causes the shock to restart, to be revived, and start flowing outwards again. This results in what is known as a core collapse supernova. The outer layers of the star are blown away by the enormous energy released during the collapse in the form of neutrinos. 99% of the energy of a supernova comes out in the form of neutrinos. Only 1% of the energy comes out as light. However, that 1% is still 10 billion times greater than the luminosity of our sun, and can actually outshine the galaxy that the supernova is occurring in for a few days. Core collapse supernovae occur at the rate of about 1 every century per galaxy. Now, we've seen a few of these supernovae close up. For example, in 1054 AD, Chinese astronomers observed a so-called guest star, a star that appeared in the daytime sky. They recorded this event, and if we turn our telescopes to that patch of the sky today, this is what we see: the remnant of the supernova, what we now call the Crab Nebula in the constellation of Taurus. This is a striking image. This is the outer layers of the stars that were blown off during the supernova and are continuing to expand to this day. As we'll see next week, the very center of this nebula lies the very heart of the star that exploded. Tycho observed a supernova in 1572 AD in Cassiopeia. This is what it looks like today. And Kepler in 1605 observed a supernova in Ophiuchus. Again, this is what it looks like today. In modern times, the closest supernova that we've observed was supernova 1987A, which occurred in the Large Magellanic Cloud. Here is a before and after photo. Okay, there was a star at the tip of this arrow here that you can just about make out if you stare hard enough at it. A few days later, this is what it looked like. It was going supernova. A few years later, this is what we see at that point. So we see the supernova remnant is the bright material expanding at the center. We also see these two rings here. If we zoom in, this is what it looks like. These two rings are actually matter that was lost from the envelope of the star, we think a few hundred years before the supernova explosion occurred. The star was obviously very massive, and as we know, massive stars are barely stable even before they go supernova. The radiation pressure dominated outer atmospheres means that their outermost layers are barely held on by gravity. So sometimes a little push is all it takes to send some material out into space. Just a few more examples of supernovae here. This is a supernova that is as bright as its parent galaxy in M51. Here's another before and after shot of a supernova in M88. And here's a supernova happening in the galaxy NGC 4526. This is what a supernova light curve happens. So if you plot the magnitude that you see, the magnitude of the supernova, the brightness of the supernova as a function of time, this is what it looks like. It gets brighter for a few days until it reaches its peak luminosity. Then it drops off rapidly before getting dimmer at a much slower rate and then getting dimmer at a higher rate again. The reason that it gets dimmer at different rates has to do with the decay of different radioactive isotopes that are produced during the supernova. Observationally, supernovae are classified according to their spectra. On the left here, we show some schematic supernova spectra of the main categories. And the key thing to look for is whether or not there is hydrogen present in the spectrum, whether there are emission or absorption lines of hydrogen that you see in the supernova spectrum. If there are no hydrogen lines, then the supernova is classed a type 1 supernova. If there are hydrogen lines, then we have a type 2 supernova. All type 2 supernovae are the result of the collapse of cores of massive stars. So shown here is a massive star with its hydrogen-rich atmosphere and this onion-like nest of shells of different elements, the leftover products of all of the different fusion reactions that were going on. So there's a lot of hydrogen here that gives you this big hydrogen emission line, hydrogen alpha emission line. Now, type 1 supernovae that have no hydrogen are further sub-classified. You have type 1A supernovae. Type 1A supernovae also show no helium lines, and they show very strong silicon lines. Now, these are actually thought to arise by a completely different mechanism, the thermonuclear explosion of a white dwarf star, and we will come back to this type of supernova, the thermonuclear supernova, in 3 or 4 weeks' time. Type 1b supernovae have strong helium lines in their spectrum, and these are thought to correspond to the collapse of stars who have lost their hydrogen atmospheres through binary interactions, and we'll come back to that in a couple of weeks' time. And type 1c supernovae, in which you also don't see any helium and the silicon lines are weak. And these are thought to be stars that have lost both their hydrogen and their helium layers and then explode. So this is summarized here. I like this chart here, which color codes the different emission and absorption lines from the different elements. And you can follow this chart in order to decide whether a spectrum that you have is that of a type 1 or 2 supernova and what subtype it is a member of. There are also differences in the light curves of different types of supernovae. So the light curve is just how bright the supernova is as a function of time. So all supernovae tend to rise to a peak luminosity about a week or two after the initial explosion, and then that light curve decays away. The main thing to look out for in the light curve is whether it decays for a little while and then around 50 days that dimming of the supernova gets less rapid, so it decays away less rapidly and you get this plateau type feature here before decaying away more rapidly again. So here the luminosity, the star is, so here the supernova is being kept brighter for longer because of energy released by the decay of heavy radioactive elements that are being produced by the various nuclear reactions that occur in a supernova explosion, more of which in a moment. Thermonuclear supernovae, however, they decay quickly at first and then they level off slightly, but there's no plateau phase that you can see in the light curve. Supernovae are enormously important for life because they are one of the main ways that a lot of the elements that are produced and required by life exist. This is a plot of the abundance of elements that we find throughout our solar system versus atomic number. So hydrogen and helium are the most abundant elements, but we see many more familiar elements here and their relative abundances on this logarithmic scale. One question that astrophysicists try and answer is, why do the elements appear in this abundance pattern? We also have to account for several features of this abundance pattern. So firstly, note that we're on a logarithmic scale here. Okay, so a difference in 1 on this scale refers to a difference by a factor of 10. So lithium is about 7.5 orders of magnitude less abundant than helium. So in other words, there's over 10 million more helium atoms per lithium atom in the solar system. Particularly, we have to account for the peaks in this abundance pattern around iron and around the rare earth metals here. So this is the rare earth peak, and around these heavy elements here. This is the heavy element peak. So you notice here there are peaks. They appear fairly weak peaks in this picture, but that's because, again, this is a logarithmic scale. The difference, for example, between xenon and barium is about a factor of 2. There is twice as much xenon as there is barium. All right, I've included another picture that kind of brings out the rare earth peak and the heavy element peak a little better. One question that astrophysicists try and answer is, why do the elements appear in this abundance pattern? Well, they get produced in a number of processes, and a lot of them occur in supernovae. So ordinary fusion in ordinary stars produces a lot of the elements up to iron, but many of the heavier elements cannot be manufactured in stars by those normal processes. They must be created by highly energetic events like supernovae. What happens is that in supernovae, there are a lot of free neutrons about. The electrons are captured by protons and create more neutrons. And so processes like the R process becomes viable. The R process stands for rapid neutron capture. And what happens is elements capture neutrons, a lot of neutrons, some of which decay into protons, and generate a number of elements up this line here. And they then decay upwards and form stable elements at a much higher mass number. So the important nuclear reactions that take us from elements up to iron to all the heavier elements that we see in nature can be boiled down to basically 2 important reactions. And the most important one is neutron capture. Neutron capture is the thing that's going to make us heavier elements. you take a nucleus and you simply capture a neutron to give you a nucleus with a mass number that is greater than 1, still the same element, so this is a heavier isotope of the element, and the process also releases a gamma ray. These reactions compete with beta decays, which take an element and one neutron in that nucleus turns into a proton. So the total number of neutrons and protons is the same, but you've got one more proton, one less neutron. And this also produces an electron, and this should be an anti-neutrino. On the chart of the nuclides, neutron captures take us to the right, beta decays take us up one and to the left. So in order for these reactions to build us heavier elements, we need to be in an environment where there are free neutrons. Now, neutrons can occur from the decay of unstable nuclides that are left over after certain fusion reactions. And so you can get some neutrons actually appearing in heavy stars, in giant stars, before they go supernova. Not many, but enough to start manufacturing certain heavy elements. But you get a lot more neutrons in supernova explosions, because in supernova explosions, the core of the star is destabilized by electron captures, which turn protons into neutrons in nuclei. And then when the temperature gets so high, those nuclei start falling apart and you get lots and lots of free neutrons produced. So there will be a link to this interactive chart of the nuclides that you can explore to your heart's content. So stars start off with the fusion products, which are below iron 56, so in this region of the chart of the nuclides, and the S process, and the important reactions are neutron captures, which, if you take a starting nuclide, just move you to the right without going up and down, so move you to more and more neutron-rich isotopes. Now, if you could just keep going with this, you eventually come to the rightmost square in a column. What happens after that? Well, after that, the nucleus is so big and neutron rich that if you try and add another neutron to it, it just falls out. It's not bound anymore. This rightmost part of the chart of the nuclides is called the neutron drip line. We talk of neutrons just dripping out of nuclei because they are so weakly bound at this point. So this is as far as you can go, just adding neutrons to nuclei. But you can't just add neutrons whenever you feel like it and create more and more neutron-rich isotopes, because these isotopes are unstable to beta decay. That's what the blue color coding looks like. If you go to key, you can show the key, and that will appear in the bottom right hand of this. Beta decay involves a neutron in a nucleus turning into a proton, an electron, and an anti-neutrino. And what this does is it takes a nucleus, a starting nucleus, and moves it up and to the left. So you're losing a neutron, which takes you to the left, but in its place you're gaining a proton, which takes you up one to the next element. So beta decays take you diagonally up and left, whereas neutron captures take you to the right. Now, if the nuclei beta decay faster than they're capturing neutrons, then anytime you capture a neutron, you're immediately going to beta decay back to the left. So you're never going to make that much progress. You're not going to make a lot of progress at one time to the right. So when there aren't that many neutrons around, that's what's going to happen. The neutrons aren't going to be captured very quickly. So every time you do capture one, you're going to beta decay back to here. And you're going to, occasionally, you might capture 2 neutrons and beta decay back like that. So you're going to gradually, by this repetition of beta decay and neutron capture, work your way up the chart of the nuclides, but you're always going to stay very close to the black nuclei here, which are the stable nuclei. So this is the line of stability. And you're always going to remain close to there because beta decays are always winning out over neutron captures. So this is called the slow neutron capture process, or the S process. However, if you've got a lot of neutrons around, like you do in the supernova explosion, then you're going to capture neutrons more often than beta decays occur. So you'll be able to undergo multiple neutron captures before the nucleus will beta decay, taking you one step up and to the left, and then you'll capture some more nuclei, and there'll be a beta decay, capture some more nuclei, and eventually you'll reach the neutron drip line, at which case you'll beta decay back and continue capturing neutrons again. So in the rapid neutron capture process, the R process, you're going to tend to create heavier and heavier nuclei, and you're going to do it fairly close to the neutron drip line. So for the S process, you work your way up the chart of the nuclides close to the line of stability, whereas for the R process, you work your way up the line of nuclei, remaining far from stability. Once you've got all the way over to the neutron drip line, there's nowhere else to go, and eventually you've used up all your neutrons, and once that's happened, then all the leftover heavy nuclei that you've created and are sat here close to the neutron drip line, if there are no more neutron captures, all they can do is beta decay. So these will beta decay all the way back up here toward until they reach the line of stability again. So you'll end up getting back to the line of stability either way. These are just two different ways you can manufacture elements. However, because of the very complex interplay between the various reaction rates, it turns out that the R process tends to manufacture different nuclei than the S process. And so you really need the combination of both the S process, which occurs in the atmospheres of giant stars, and the R process, which occurs in supernova explosions, to create the full periodic table of elements that we are familiar with. So to summarize these processes, the R process, which stands for rapid neutron capture process, requires lots of free neutrons around so that they get captured at a faster rate than beta decays occur. This drives the production of heavy nuclei near to the neutron drip line and drives the formation of neutron-rich nuclei up the neutron drip line. It isn't so obvious here, so this is a better picture which shows the R process driving nuclei towards the neutron drip line by neutron captures, then beta decays take them in, more neutron captures take them back to the drip line, and so on. And then when all the free neutrons are used up, the remaining isotopes that have been produced beta decay back towards the line of stability. This is in contrast to the S process, the slow neutron capture process, in which neutron captures occur at a slower rate than beta decay, and the trajectories, the shape of the trajectories on the chart of the nuclides look the same as for the R process, or look very similar at least, but they happen close to the line of stability. You never get nuclei driven towards the neutron drip line because beta decays happen quickly enough to always take you back towards the line of stability every time you make a neutron capture. The final thing we need to account for is the presence of these peaks around iron, the rare earth metals, and the heavier elements. And to do that, we need to understand a little bit about nuclear structure. And the basic thing we need to understand is that neutrons and protons in nuclei occupy energy levels, or orbitals, or shells, if you like, in a very similar way to electrons in atoms. And when you calculate the energy levels of neutrons and protons in nuclei, we tend to arrange them and give them names in a way that is analogous to electrons in atoms. So you have the prime quantum number, or the orbital quantum number, which here is 1, 2, 3, and so on. Then the angular momentum quantum number, S, P, D, F, again, just like for electrons. There is, the details are different, however, and affect how many neutrons and protons you can store in a given energy level or shell. It starts off similar to electrons, so you can put 2 neutrons or 2 protons in the first energy level, 6 in the next angular momentum energy level, which takes you up to 8, and then a further 12 in the next set of energy levels, which takes you up to 20, and so on. So you get shell closures at 2 nucleons, 8 nucleons, 20 nucleons, 28, 50, and so on. Okay. This applies to both neutrons and protons. The neutrons and protons occupy their own independent set of energy levels. And just like with atoms, nuclei are particularly well bound when you have exactly the right number of neutrons or protons to fill a particular energy level. Okay, so helium is particularly stable as a nucleus because it has 2 neutrons and 2 protons. So both the neutrons and protons fill this first energy level. Oxygen is the next really stable nucleus because it has 8 neutrons and 8 protons. So they both fill up to the second energy level here, the 1p energy level. Calcium is the next really stable nucleus, and so on. The next one after 50 is 82, and the next one after 82 is 126. So if you look where these numbers occur on the chart of the nuclei, they're drawn here with the vertical lines. And because nuclei around these so-called magic numbers, that's what nuclear physicists refer to them as, because the nuclei there are particularly stable, when you are creating heavier nuclei via the R process or the S process, and then beta decays take you back towards the line of stability, then nuclei are going to accumulate around these magic numbers, right? So you're going to get more nuclei produced with magic numbers around or just below 50, around or just below 82, around or just below 126. Why just below? Well, because if you get nuclei produced that aren't quite stable at 126, say neutrons, then beta decays will take them up and to the left, and you'll end up with stable nuclei that have numbers of neutrons just under 126. And so around the numbers 50, 82, and 126, that's where these peaks occur. That's where these rises, these peaks in abundances happen. This is a simulation of how the R process forms heavy elements in the latter stages of a supernova explosion. So we see here the chart of the nuclides. The nuclei that we start with are shown down here in the blues and the greens. The color indicates their relative abundance. The bluer it appears, the less abundant it is. Greener, and as we'll later see, oranger and redder are successively larger abundances. So these are the so-called seed nuclei, the nuclei that we end up with as a result of fusion in the star. The black squares show all the nuclei that are stable, and these vertical lines show the neutron shell closures at 50, 82, and 126. So if we set it going, what happens is that these nuclides start capturing neutrons and creating more and more neutron-rich nuclides and driving them further over towards the neutron drip line. So creating more and more neutron-rich nuclei by these neutron captures which are happening quicker than beta decay can get rid of them. But once we've gone as far as we can, then all that's left to do is beta decay the produced nuclei back towards the line of stable nuclei here. And so in this latter stage of the simulation, you're seeing beta decays returning all the products back to the line of stability. And we see we get the rare earth peak here and the heavy nuclear peak here as the result of decays, beta decays from nuclides that had filled nuclear valence shells. So to summarize, stars can only manufacture elements up to iron through fusion reactions in their core. Most of the rest of the elements in nature are produced as a result of neutron captures. So some free neutrons exist in giant stars as the result of fusion products from the fusion reactions in their core, and these drive the S process, the slow neutron capture process, whilst enormous temperatures and energy that are released in supernovae can cause the productions of heavier elements through the R process, the so-called rapid capture process. We're now going to discuss a few more details of these reactions. This is a useful version of the periodic table. This is color-coded to tell us where in the universe these elements are actually created. As we'll see, the Big Bang actually creates all the hydrogen and helium in the universe. The light elements, like lithium, beryllium, and boron, are created by a mixture of the Big Bang and cosmic ray interactions. We'll deal with that a little later. But most of the rest of the elements are created in large stars by ordinary fusion processes, or via the S process, or by supernovae. So for example, all of the gold and platinum and iridium that exists, we think, because of supernova explosions. I'll leave you with a summary of stellar evolution. This just summarizes the mass of the star, increasing mass going upwards, what it ends up evolving to. So if the protostar starts off massive enough, it will ignite fusion in its core, and you'll get a sun-like star, evolves to a red giant and a planetary nebula and a white dwarf. Heavier stars will go through a blue supergiant and then a red supergiant phase, before undergoing core collapse supernova and ending up as a neutron star, something we'll explore next week. Even heavier stars go through a blue supergiant phase, a type 2 supernova, and end up as a black hole. Even heavier stars may go straight to a black hole from the blue supergiant phase without even passing through a supernova explosion. The most massive stars may end up in a supernova so catastrophic that it blows the entire core apart and leaves nothing behind whatsoever. All the material that gets left behind from the planetary nebula through the supernova remnants drifts off and becomes part of the interstellar medium that becomes part of the new stellar nursery that produces the next generation of protostars and the next generation of stars, and the cycle of life is complete.